Welcome to our lecture online, and now we're going to do something really interesting. What we're going to do here is we're going to take a block of ice, 10 kilograms at 0 degrees centigrade, and infuse enough energy to take that block of ice and melt it into 10 kilograms of water at the same temperature. Well, because the latent heat of fusion, that takes a certain amount of energy. Now the question is, when we infuse that energy into the ice, will that cause the mass of the ice to increase by the amount dictated by the equation E equals mc squared, which would mean that the block of ice would have increased in mass by the amount of energy we put into it to melt it, divided by the speed of light squared. We already know that that happens in nuclear reaction, in nuclear fusion reactions or fission reactions, when nuclei are either fused together or broken apart, fissioned into smaller nuclei, that energy is produced, and the amount of energy produced is equal to the difference in the mass of the products initially, and then the difference between the initial products and the final products. And so we're questioning if that's the same case here. And if it is, what would be the change in that mass? So let's go ahead and find out. Well, how much energy is required to melt a block of 10 kilograms of ice? Well, we know that the latent heat of fusion is equal to 80 calories per gram of ice. And let's see here, let's convert that to joules. We know that the number of joules per calorie is 4.186 joules per calorie. And of course, we don't have 1 gram, but we have 10,000 grams, because that would be 10,000 grams of ice. So this is the amount that would be for 1 gram, but this would be the amount that would be for 10,000 grams of 10 kilograms. So that's the amount of heat that had to be added to the block of ice in order to completely melt it into water. So let's go ahead and find out how much that is. So starting out with 80 calories per gram times 4.186 calories per joule, or joules per calorie, times 10,000. That ends up being 3.348 or 3.349. So 3.349 times 10 to the 6 joules. So about 3.3 million joules of energy required to melt the ice. Well, how much mass is that? Well, let's go ahead and throw it into the equation. So delta M would be equal to the energy, that would be 3.349 times 10 to the 6 joules, divided by the speed of light squared at 3 times 10 to the 8 meters per second, quantity squared. And the amount of mass increase, because when we add energy to it, we'd expect the mass to increase. The amount of increase in mass would be divided by 3 e to the 8 squared equals, let's see here, that would be 3.72 times 10 to the minus 11 kilograms. Well, take a look at that. About 4 times 10 to the minus 11 kilograms, that's about 40, not nano, but picokilograms. That is such a small amount that there's no way we'd be able to measure the difference. On a 10 kilogram block of ice turning into water, there'd be no way that we could measure this difference in mass. However, if it is true that adding energy or taking energy away would either increase or decrease the mass of the substance, and it's this much, then of course that would then match with what we learn in relativistic physics, is where things happen at the nuclear level, where the difference in mass is measurable. We are indeed able to prove that this is true for those nuclear reactions. Is it true for something like this? We can only assume that it is, because it would then hold true with the laws of physics, but we want to be able to experimentally measure it and verify this. So anyway, there you have it. That's what it would be if we were to melt a block of ice of 10 kilograms down to water. We'd have a change in the mass by 3.72 times 10 to the minus 11 kilograms.